Good day everyone. So this is the module 2 of IE303 or 303L Ergonomics 1, first semester. So the principles and practices of anthropometry. This study guide discusses the definition and importance of science of anthropometry and its application in designing products and other work system components to fit the target users of the systems. This is a very important topic in ergonomics because as industrial engineers, we are opt to design workplaces and as well as those tools and materials that are needed by our workers so that we can design them according to the characteristic of our worker. Okay, so the topic shows real-life applications of using anthropometric measurements in designing products, workplace design, and other industry applications. This lesson guide in anthropometry will help industrial engineering students to develop skills in identifying poorly designed systems and its effect to workers' well-being and overall performance. Accordingly, this module will aid the students to demonstrate an application of their acquired learning of the anthropometry. So at the end of this course, you will be applying your acquired knowledge. Okay, so let's go to the duration and the learning objectives. So the duration of this module is 6 hours. So for the learning objectives, at the end of this module, student will be able to define anthropometry, discuss the importance of anthropometry, identify the necessary anthropometric data for a given design, differentiate static from dynamic measurements, accurately measure body dimensions in steady and action state, identify the best design principle for a specific application, correctly compute for the necessary statistics in an anthropometric design, identify the effects of poorly designed systems, and identify real-life applications of engineering anthropometry. Okay? So before anything else, I want you to watch this video so that you have a prior knowledge about what is anthropometry is all about.
Anthropometry is the study of human dimensions.
Everything from body fat percentage to the length of your nose can be considered anthropometry.
For this section of testing, we have 4 measures.
First is height, without shoes.
Then arm span and hand span.
The key takeaway from these tests is the ratio between your height and arm span. An arm span longer than your height is usually best, as is a larger hand span.
And last is body weight.
Body weight alone doesn't actually tell you much. Negative things like dehydration or having low glycogen stores can actually reduce your weight, while positive factors like gaining muscle mass, or if you're a junior, just growing taller, is going to have a positive effect on your performance, but your weight's going to go up as a result. What body weight does give you though is a general radar for your health. Smooth, gradual, even fluctuations in body weight are much more conducive of high performance than sharp peaks and troughs.
Okay, so I hope you gained some insights by watching that video about anthropometry. Now let's go to the lesson content. So there is a statement here. We found out that airplane manufacturers are still building airplanes the way they want, but God is not making people to fit them. This statement is from a story that appeared in Washington Post May 25, 1984. So it only implies that the airplane manufacturers should design their airplanes based on people who are using it. Okay, so they should take into consideration the characteristic of people, because the characteristic of people cannot be adjusted. Okay, cannot be adjusted to use the airplanes. Okay, but the design of the airplanes can be adjusted. Okay, so next, we have defined from the last module that ergonomics focuses on designing work systems, right? That fit the workers rather than forcing the workers to adjust and adapt themselves to the different components of a work system, right? So that's what we have discussed in the last module. So however, in order to design things that fit the human body, it is important to know the characteristics and particularly the body dimensions of people who will use the system. Of course, before we design any system or any design of product and equipment, we have to know what is our based information. Okay, so what information we are basing. Okay, so we should base on the user's characteristics, which lies in anthropometry, because the users are the one to use uh, the objects that we will be designing. Okay, so in addition, consideration of human body characteristics, capabilities, and limitations. So not only characteristics, but the capabilities of human should be considered here, and as well as their limitation helps the designers as industrial engineers. We are a designer to develop equipment, tools, and other work system components that can maximize human strengths. Anthropometry is one of the fundamental topics in ergonomics that can help in reducing the mismatch between the work person and work system components. So this topic is fundamental to our subject. So it is important for us to have a good knowledge about this. Okay, so let's go now to the definition of anthropometry. Anthropometry is simply defined as the science of measurement of physical geometry, mass properties. It is physical because here we will be measuring the arm span, uh, the palm span, okay, our height, okay, etc. So about our physical characteristic. Geometry, because the shape of our body parts matters, okay, when designing an object for us to use. Okay, so mass properties. So what are the properties of mass? There are many properties of that. It's lightness, okay, heaviness, etc. Okay, and strength capabilities of human body. So what are the strengths of your user? So we can study them in anthropometry. So the term anthropometry is derived from the terms anthropos, which means human, and metrikos referring to measurement. That's why it is a study of human measurement. So the science of anthropometry is concerned with collecting data of human body sizes, proportions, as well as other related characteristics, which are essential in determining the right dimensions for the designs of devices, equipment, and other work system components. Why do you think that body size proportion is important? It is important because when designing a product, it should be balancing, okay, balancing uh, the body proportions of the user. For example, if you are designing a device, it should be light, okay, because a user can lack for enough strength to carry it. Okay, so it should be proportional to the body of the user. Okay, so other applications are observed in design evaluation of vehicles, workplaces, and in clothing industry. So these are other applications. You can work as an industrial engineer in a uh, car manufacturing company. Okay, so we can use anthropometry there. Then workplaces, of course, and in clothing industry. Okay, so the science of anthropometry originated from anthropology, with with focus on the study of mankind. So it is where it was originated. So particularly the basic concepts are derived from physical anthropology, which is a subdiscipline of anthropology. Okay, so that deals with the measuring and comparing human body parts, most especially human bones. Okay, why do we consider human bones here? Okay, so because human bones are one of the most fundamental parts of human body that a human use for work. Okay, so the beginning of modern anthropometry was recorded in 19th century when Adolf Quetelet, a Belgian statistician, firstly integrated statistics to the collected anthropological data. So that is the origin of anthropometry. So next, it is very important to classify the subjects for data collection of anthropometric measurements. Why? Because when we fail to classify the subjects, uh, we tend to we tend to produce a confusing data. Okay, so classification of kinds of subjects or users must be considered. Okay, for example, when we are going to design a product, what users it is intended uh, to serve. Okay, the young age or the middle age or the old age. So we should classify our objects of design for designing. Okay, or the subjects or the stakeholders of what we are designing. Okay. Next, primarily, the military has always been the subject participants for data collection of anthropometric measurements since its early applications were seen in fitting of military uniforms, armors, and other equipment. Why military? As we mentioned in our last discussion, ergonomics and uh, other sciences originates during World War. Okay, so the military personnel needs them the most because uh, they need accurate equipments. Okay, that make them comfortable and more safe. Okay, more safe in the battlefield. Okay, so however, it has been realized that anthropometric data of military subjects should not be applied in designing products intended for civilian population. It is true. That's why we classify our subjects, okay? For the reason that military people are generally young and in healthy physiques as compared with ordinary civilian group. That is true. So similarly, anthropometric data of civilian from one nationality should be used with caution when designing products for people from different nationalities. It is true again because our body physics as Filipinos are different from the body physics of the Western people. Okay? So they are more huge than us or bigger than us. So next, some typical example of poorly designed products and work systems which can be addressed by proper application of anthropometric data are sinks that are too low. So those sinks, if you have one in your house, if you feel it is too low, you can use this principle or this subject to repair that. Okay, so handrails, what are handrails? That are too high and too high, so those handles, okay, it should be properly elevated for the user, okay, that fit the hips and pants that fit the hips but are too loose at the waist. So those are common, okay. So in general, the science of anthropometry in ergonomics is considered as one of the fundamental tools in analyzing and developing engineering design properties. Okay, so that's why it is very important. Its application is important in order to design workplaces, equipment, and other work system components that are compatible with the characteristic capabilities and limitations of workers. As I mentioned in our last discussion, as industrial engineers, we are very well flexible in our field. We can be a workplace designer, a product designer if we are assigned in product and development department of a company. Okay, so uh, this topic is very important for us. Okay, so next, there are basic knowledge and skills necessary in collecting anthropometric data. First, familiarization on human anatomy to identify different body segments. Of course, we should be familiarized with different body segments so that we can identify them when measuring. Okay, so next, proper reading, handling, and utilization of measuring devices and instruments. Of course, we cannot measure correctly if we do not know how to use them. Okay, those measuring devices, and statistical principles and methodologies, because the gathered data that we will get, we will apply statistical principles and methodologies to them. Okay. Next, mathematics concepts of mass, properties, force, and torque. They are also considered here. Okay. So those principles, science principles, we will be considering them. Okay, mathematics and science principles. So next, planning and organizing time and processes. Yes, we have to consider that because uh, the process of getting the measurements and processing them should be planned. Okay, and everything we do, we should plan and organize. Okay, in accordance to the time value. Okay, so next, good language skills and facility in writing scientific material. Okay, this applies to making reports. Okay, so after we gather data, we process them. Okay, we have to make reports, so we have to have a good language skills. Okay, next, statistical description of human variability. So the figure below shows an example of normal or Gaussian distribution of collected anthropometric data for stature of adult British men. Oh, so this is for British, okay, British people. We all know that those Westerners are larger than us, okay? So this won't apply to us. But for the sake of discussion, because this is well known around the world, we have to discuss this, okay? So figure 1, the frequency distribution or probability density function for the stature of adult British men. Okay, night it is 1984. Okay, the frequency of occurrence for standing height of adult men is plotted against the stature in horizontal axis. So that's what makes that is what makes this figure 1. Okay, so the probability density function for the frequency distribution, it is illustrated using a smooth curve in graph. Okay, what is a smooth curve here? So when you say smooth curve, it is the curve like a bell shape. Okay, it has a smooth curve. Okay, that is the graph. So the curve is considered a normal distribution because it is in bell shape. Okay, remember our topic in statistics. Given that it is bell shaped and symmetrical on both sides. Okay, it is symmetrical because it's like a mirror. Uh, when you uh, when you separate the right side and the left side, it will be equal. They are symmetrical. So most anthropometric data are normally distributed. So it suggests that 50% of the population is taller than the average stature and 50% is shorter than the average stature. So why is that? Okay, because another 50% is in the left and 50% is in the right. So that is why. Okay. Next, going over the explanation of percentile in descriptive statistics, it pertains to a certain percentage of values that fall below a specific number in data set. Okay, so there's only specific number in data set for this percentile. Okay, referring to figure 1, it follows that there is a point in left hand and along the horizontal x that indicates the 10th percentile value, representing the 10% of the adult British men are shorter than 1,650 millimeters stature or standing height, and accordingly 90% of the people are taller than this stature. So these measurements, this percentile is just taken from this graph. Okay, do you recall our topic about percentiles, getting the percentiles uh, of a data, okay, in the graph? So that's it. So similarly, 95th percentile refers to 95% of the population shorter than 1,850 millimeters stature. And there are 5% people taller than this stature. It is also important to note that 5th and 95th percentile encompasses the 90% of the population. So when you take a study for Filipino people, of course you will use another distribution for Filipino people. You cannot use this one, okay? And then to have your reports or documents, you need to apply this concept, the percentile. Okay, so uh, to describe more properly or accurately the findings of your data. Okay, so next, design limits. In practice, it is recommended to design for the 5th to 95th percentile range. So remember that, okay? To accommodate for the middle 90% of the user population. So, however, the designer still needs to re-examine the associated consequences of the mismatch for those who fall outside the design limits, which over 10% of the target population. Of course, we have to be at least 90% and up, 95% and up, sure that 90% and up sure that our design will fit our population. Okay, so the designer should reevaluate whether this mismatch could result to discomfort, inconvenience, health, and safety of the users, or might compromise the overall system performance. So that is another study. Okay, so emphasizing the health and safety, the designer has critical decision on setting the design limits. For instance, you are tasked to specify the dimension of an escape door. Escape doorway. What is escape doorway? It is used for emergency. Okay, when there is a fire on an establishment, escape doorway is used. Okay, for getting away from the fire. So from a confined working area, setting the design to 99 percentile would mean few people would experience trouble in passing through the escape door. Why? Because uh, based on our uh, based on the statements a while ago, 90%, okay, 90% is our base, okay, here 90%, in the middle of 90% is our base, so increasing it to 99% will make uh, some of the population uh, have some trouble, okay, have some trouble in passing them. So we have to consider them also, okay? So therefore, the designer must take extra caution because including even one person, so even one person, okay? So we should consider it. In safety critical situations would not be acceptable, okay? Because in most company, if you do not know, uh, most companies, for the first aim of most companies is safety. That is why it is dubbed as safety first. Okay, any company, they implement safety first. Okay, so it is very important. Next, constraints of anthropometrics. So what are the constraints or the factors? So basically, there are four fundamental constraints of anthropometrics that are important setting design limits. So we have four. First, the clearance determines the minimum acceptable dimension in the object. Okay, so the clearance, it should have enough clearance. Some examples of clearance constraints are adequate space for headroom, okay, for moving well, okay, adequate space, elbow room, okay, for avoiding elbow injury, then leg room as well as with leg injury, thigh clearance, okay, so that the worker, the user can move, and small opening for fingers or palm for handles, okay, so that everything or every part of a user can move, okay, freely. So in practice, these dimensions consider accommodation of bulky member of the user population. So mostly it is used. For instance, considering 95th percentile height and breadth follows that 95% of the population is smaller and would be accommodated. Okay, so that's the consideration there. Next, reach determines the maximum acceptable dimension of the object. So first is clearance, next reach. So example of reach constraints are height of seat surface. So the height of the chairs that we are going to design. Okay, its distance from the surface and allowing individual to grasp and operate controls and equipments. So meaning the chair should be positioned where the controls and equipment are near. Okay, so that they don't have to reach hard. Okay? So this constraint often needs one setting requirement and considers the small member of the population. Let's say the designer considers fifth percentile popliteal height for seat surface height. It follows that 95% of the population taller than fifth percentile popliteal height would be accommodated on the design limit. So this reach category, okay, or this reach constraint uh, just comes with the fifth percentile, okay? Because when you design for the fifth percentile, when you design for the 5th percentile, uh, it is likely to be uh, good also for the 95%. Okay, so they have their percentiles. The clearance is for 95%, reach is for the 5th percentile. Okay, you should remember that. Next, posture, the result of the degree of compatibility between the dimensions of the body and those in workstation. Yes, number 3 is posture. Third constraint, because it is the result of the compatibility. One cannot have a good posture if his characteristic is not compatible with his work environment. Okay, so a typical example of posture constraint is when a working surface is too high for a smaller group, because when a smaller group of users use a high table, for example, they tend to exert effort in uh, looking upward, okay, that will give them some hard time, okay, and will cause them some pain in the neck, okay. So, or when it is too low for taller member of the population, so the other way, okay, the users are are taller, then the work workstation or the workpiece should be uh, elevated to them, okay, or in their height. So this condition will result to poor working posture, okay, as this constraint is influenced by the dimensions of the work system components surrounding an individual. So that will result to poor posture, okay. So how many? So that's the third. So next, fourth. Fourth is strength, okay, refers to the level of force that is acceptable to weak limiting user. So two setting requirement for accidental operation of a control. Okay, so when we say strength, we have also to consider those accidental operation. Okay, so our design should uh, cater for some instances of accidents, okay, of operation. So one example of considering constraint is determining the acceptable wrist twisting strength for jar opening design. Okay, so when you suppose you are designing a jar of opening, okay, so you have to consider the the strength. Okay, so too much strength can break the jar. Okay, so you have to devise some mechanisms that caters of excess strength. Okay, so however, in accidental operation of controls situations, the designer of the system must also consider the characteristics of heavy-handed or heavy-footed individuals. Okay, because heavy individuals will exert more strength. Lighter individuals will exert more or less, okay, lighter individual will exert less strength. Okay, so next, principle of limiting user. So limiting users represent both tails of the frequency distribution of anthropometric measurement. So what do we mean by limiting users? They are the users that fall on the limits. Okay, the limits. That's why the tails of the frequency distribution are mentioned here. Okay, they fall on the limits. Okay, so it refers to the hypothetical members of the user population who often dictate the most severe constraint, okay, on the design of an object due to their physical or even mental characteristics. Okay, so they are the special ones. Okay, uh, they are the most critical consideration. Okay, and even the mental characteristics, because we have discussed in our last lesson that not only physical but mental characteristics are involved here in ergonomics. Okay, for instance, bulky person is the limiting user for setting clearance, and small person is limiting person for determining the design limit for reach. So that is not good, because if you limit the bulky person, it will not suit the small person. If you use the bulky person as the limiting user for the setting clearance, it will not suit the small person. So you should have considered small person. Okay, you should design it in their middle. Okay, middle size. Okay, so next, plotting corrections and using anthropometric data. In practice, anthropometric data are measured and collected with an cloth people or with minimal clothing. So when we are measuring or getting the anthropometric measurements, so those clothes should be taken away, okay, to avoid destruction. So on the contrary, products or work systems are often used by cloth individuals. Thus, it is important to add appropriate clothing correction and using anthropometric data for setting design limits. So, in reality, uh, workers use clothing just like the gloves. Okay, for example, uh, a mechanical worker use gloves. Okay, to protect his hands. So we should also consider the the measurement of the thickness of the gloves. We should include it in our measurement. Okay? So FESAN 2003, it is a study, recommend the following adjustments. Okay? For men, add 25 millimeter to all dimensions. So when you measure all the parts, you should add 25 millimeter. And for women, add 45 millimeter to all dimensions. Okay? So those are the standards of this study, FESAN 2003. Nevertheless, clothing corrections may increase if necessary, most especially when the workers are required to wear thick clothing protections for PPEs. So that is true because personal protective equipments sometimes are very thick, okay, in order to protect the user. So those requirements shall be considered. Okay, next. Standard anatomical position. So standard standing posture, the subject stands straight, pulling herself up to her maximum height and looking straight ahead. Her shoulder should be relaxed and full arms hanging loosely by her side. So when someone is standing, we should design the workplace with that, okay? Should be comfortable. So next, standing sitting posture, the subject sits erect on a flat and horizontal surface, okay? So that thighs are parallel to the floor. So the thighs are parallel, meaning in a neutral position, okay? Not twisted. Lower legs are in vertical position, neutral again. And he or she pulls herself up to her maximum height. So he can stand in his maximum height. So we should avoid low ceiling and looking straight ahead. So we should avoid obstructions, okay, in sight. So her shoulders should be relaxed and upper arms hanging by his sides and forearms are in horizontal position. So proper spacing, okay. So next, four customary positions. So first, standing naturally upright. Okay, so you should remember this. These are the most or the customary positions. So standing stretched to maximum height, leaning against a wall with the back flattened and the buttocks, shoulder, and back of the head touching the wall. So those are the positions we're measuring. So lying on the back. Okay. Next, head in Frankfurt plane. So what is that? In head in Frankfurt plane exhibits a posture in which the head is in a straight position and ear-eye line is in 15 degrees against the horizontal axis. The Frankfurt plane was introduced in Frankfurt am Main, Germany in 1984. So even that small detail we should consider, okay? So what is application for uh, example for the control room, okay? So when you design a control room, the monitors, okay, as well as the controls should consider this, okay, so that our worker will uh, work efficiently. So consider this drawing. So next, body planes and orientation. Okay, so there are planes for each body and how they are oriented. So anthropometric measurements use the following standard references planes with intersect at the central mass of the whole body. As you can see, the medial or the mid-sagittal, okay, it is here on the top, so horizontally, okay, from one ear to ear or one shoulder to shoulder. Next, the frontal or coronal. So the frontal, okay, you can see in the drawing, it is right here, okay, in the lower part, okay, it is a plane from one knee to another and one shoulder to another. Okay, so next, that transverse planes. So this is the transverse plane. It is a plane from the thigh. Okay, next. So factors in defining the target population. Okay, so these are the factors. There are many primary factors which are necessary in defining target population before collecting anthropometric data. We should also consider the sex, the age, nationality, ethnicity, okay? So occupation, social class, issues relating to safety critical applications, because uh, different applications gives different safety hazards, okay? So we should consider that. So baseline definition. So what is height? Height is a straight line, point to point, upright. So the person to be measured should be upright. Body move measurement. Example, stature, eye height, shoulder height, fingertip height, knuckle height, and popliteal height. Okay, so those are many other references for the height. Okay, so when you say popliteal, it is in the back of the knees. Okay, the measurement in the back of the knees. So next, breadth, a straight line, point to point, horizontal. So this is a horizontal measurement along the entire body or body segment. Of course, there are some references again. Example, shoulder breadth, hip breadth, and head breadth. Okay. Next, depth, a straight line, point to point, horizontal measurement running force and aft the body. Okay, so depth, example, chest depth, okay, the height of the chest, so it is chest depth. Abdominal depth, okay, if the abdominal of our user is big or small, okay. Next, the distance. Distance is straight line, point to point measurement between landmarks on the body. Okay, so important here, guys, is you have the uh, points, okay, the from two points, okay, from where you are going to measure. Next, curvature, a point-to-point measurement following a contour. So this measurement is usually neither closed nor circular. So uh, when you say curvature, it involves some contour or for the shapes, okay, or for uh, the shapes of the body. That is why it involves a contour. Okay. Next, circumference, a close measurement that follows a body contour. Okay. So hence, this measurement is not circular. Why it's not circular? Because it follows a body contour. Maybe a body contour is not circular. Okay. So different individual, different contour. Okay. So next, reach, a point-to-point measurement following the long axis of the arm or leg. So it is with reference with the arms or legs. Next, anthropometric statistics. Basically, there are two important parameters used in anthropometric statistics. So what are those? These parameters are mean and standard deviation of a data set. So it uses those parameters, mean and standard deviation. Statistical mean, or the fifth percentile, is simply the average a data set, and determined by dividing the summation of numbers by a total number of values in a set. So I know that you know already that. Okay, standard deviation measures the degree of variability of numbers in a data set, or how values in data set are deviated from the mean. I know that you already know that, okay? Because we have tackled that in our statistics. So since average values are not important in designs, we have discussed that percentiles are used in determining the right anthropometric data for setting the design limits. So it is often that we use percentiles here. So in order to calculate a percentile value represented by small letter p of a normal distribution, the following parameters are needed. So m is equal to 50th percentile, or the mean. Okay. Then capital letter S and D is equal to the standard deviation. Small letter k is equal to the factor for percentile. Okay. So we have the table 1 factor of k for percentiles. We can use the table. Okay. So if percentile value, or if p is below the mean, then p is equal to m minus k multiplied by SD. Okay? Next, if p is above the average, okay, so it is below or above. So P is equal to M plus, we will know plus, KSK times SD. Okay, so you should remember this formula. Next, the desired percentile value is computed by adding the product of standard deviation, okay, and factor K to the mean if above 50th percentile. That's what the formula is saying, okay? Or subtracting the product of standard deviation and factor K from the mean if the required anthropometric value is below 50th percentile. So that's the description of the formulas. Next, table 1 summarizes the corresponding value for factor K. So we can use this table for computing percentiles given the mean and the standard deviation. Okay, table 1, factor K for computing percentiles. Okay, so you have that. So for instance, suppose you want to determine the 95th percentile of the distribution of anthropometric data. So this percentile is above the average, of course, or 50th percentile. Therefore, the corresponding factor is what? 1.65. So why is that? Because it is the corresponding factor, okay? For 95, correspond to 1.65, okay? Next, table 2, example of locating factor K, okay? So for certain applications in designing products or workplaces, it may be needed to add or subtract dimensions. Okay, so why is that? There are instances, especially in designing products or workplaces, that the designer needs to add or subtract different body segments to arrive at a desired dimension. In this case, there is a way to compute the difference between the two distributions of anthropometric data. This situation is when we are considering for another 5% of the population. Okay, so of course we are considering them also. So this will be its computation. So m sub z is equal to m sub x minus m sub y. So what are those? Where m sub z is the difference in mean, okay, of two distributions of anthropometric data. Then m sub x is the mean of anthropometric data for longer body segment. Okay, so m sub y is the mean of anthropometric data for shorter, okay, body segment. So next, the estimated standard deviation of the summed distribution z is SD sub z is equal to the quantity of the square of SD sub x plus the square of SD sub y minus 2 times r SD sub x SD sub y. Okay? Uh, multiply by 1/2. Okay? So where SD sub z, estimated standard deviation of the sum distribution z. So that's it. So SDX is the estimated standard deviation of first anthropometric data contribution. Okay. Later we will apply this. Okay. So SDY is the estimated standard deviation of second anthropometric data distribution. And R is the correlation coefficient. So we will compute for it of the distributions of anthropometric data. Likewise, to compute for the summation of two distributions of anthropometric data, m sub z is equal to m sub x plus m sub y, where m sub z is equal to the difference in mean of two distributions of anthropometric data. M sub x is the mean of first distribution of anthropometric data. M sub y is equal to the mean of the second distribution of anthropometric data. Then the estimated standard deviation of the two distributions z is, so they are just the same with the ones we discussed earlier, but differ in what? They differ in the operation. So this operation is addition, okay? Where SD sub z is the estimated standard deviation of some distribution z. Next, SD sub x is the estimated standard deviation of first anthropometric data distribution x. SD sub y is the estimated standard deviation. So it is the same, okay, up to r. The same of the first, okay? So observe that it is necessary to consider the relationship of two datasets, which indicate the degree of relationship of two body segments. This measure is represented by the use of person correlation coefficient R. Do you remember the formula of person correlation R? So we can use our scientific calculator to get that also, okay? The value of correlation coefficient, small letter r, varies from -1 to +1 with the following degrees of correlation between two datasets. Do you recall these descriptions? If the coefficient correlation r is between +1 to positive or -1 to positive or negative 0.91, it is very high correlation. Up to positive negative 0.21 minus positive negative 0.00, it is negligible correlation. Okay? So next, in terms of the association between the anthropometric data of two body segments, the following persons correlation coefficient are recommended. So this is the source, www.dind.nl, so you can visit that. So for two length dimensions and two width dimensions, the estimated value of R is 0.65. And for two depth dimensions, so these are estimations, okay guys, so that you can have uh, your value of R already, okay? R is equal to 0.20. Next, for a depth and the length dimension, R is equal to 0.20. For a width and the length dimension, R is equal to 0.30. And for a depth and a width dimension, R is equal to 0.40. Okay? Another concern in collecting anthropometric data is the number of samples for the result to be statistically significant. Of course, in the statistic process, we should consider the number of samples for our study to become significant or for the result to be significant. Okay, in order to determine the sufficient number of respondents for anthropometric measurements, we can use this formula. Okay, so n is equal to the square of the quantity z multiplied by sd all over c squared. So what are those? So sd again is the standard deviation, c is the precision, and uh, z is the z-score, okay, in the table, z-table, for desired confidence level. So what is precision? Okay, so precision is the desired measurement that we want. So in this example, you will know that. Okay, for example, you are planning to gather anthropometric data for waist circumference to be used as basis for clothing. Okay, you have collected initial number of anthropometric measurement for waist circumference, and you want to validate if there is a need to collect more anthropometric data. Okay, because sometimes we are left in the middle of nowhere if we have to get more or we have to stop. Okay, so this is what we need. Okay, to avoid being in that situation. So the waist circumference mean, so the mean is, for example, you got a 802.9 millimeters. Standard deviation, you got 81.8 millimeters. And the desired precision. So this is now the precision. So 1.5% multiplied by 12 millimeters. Okay. So it depends. The precision depends on what you are working. Okay. So desired confidence level, 95%. Of course, so z is equal to 196 if 95%. So we just substitute those values in our formula. N is equal to the square of what is 1.96, it is the z. What is 81.8, it is the standard deviation. All over what is 12, it is the desired precision. Okay, it is squared. Okay, so it's equal to 179 random respondents. Okay, so that's how you get the required number of samples. Okay. Next, sample applications of anthropometry. Case number 1, keyboard height above the seat. So this case is about application of anthropometry when it comes in designing keyboard height above the seat. So the task is establish the surface height of a keyboard so that the sitting operator has the forearms and her end wrist horizontal. So we have to know what is the height of the chair for the user to have his forearms and wrists horizontal. So the elbow height above the seat pan, females have a mean of, so these are the measurements, 220.5 millimeter with standard deviation of 26.8 millimeter. The corresponding numbers for males are 230.6 millimeter and 27 millimeter respectively. Okay, the application factor used to calculate the 10th and the 9th percentiles is 1.28. So it is the application factor. Okay, so solution. The height of the key tops should be adjustable from 186 to 265 mm so that the adjustable range is 79 mm under the given assumptions. Okay, why it is adjustable? Okay, because to cater for the adjustable range, which is 79 mm under the given assumptions. Okay, for the female 10th and the 90th percentile, okay, so 10 percentile is equal to 220.5 minus, we will now multiply the uh, multiplication factor, which is 1.28, with the standard deviation for what? For females. Okay, so we have the 10 percentile to 186 millimeters for female. Then for the 9 percentile, we just add 220.5 mm, the mean for females, to the product of what? To the product of the factor and their standard deviation. So the 90th percentile is 255 millimeters. So you notice, guys, that when it comes to the 10th percentile, it is subtraction. Okay, and when it comes to 98th percentile, it is addition. Okay, so take note of those computations. So for male, 10th and the 9th percentile, okay, so 10th percentile, 230.6, it is the mean for male, minus, because it is in the 10th percentile. So the factor, 1.28, multiplied by the standard deviation, 27.2. So the resulting 10th percentile for men is 196 millimeters. Then for the 98th percentile for male is 230.6, the mean. So it is 98, so we will add, okay, the product of the factor 1.28 and the standard deviation 27.2. So the 98th percentile for male is 265 millimeters. Okay, so you have it. Okay, you have those measurements when you are designing waist. Okay, waist measurement for clothes. Okay, next, case 2, arm length. Okay, how do we use the computation in arm length? So task, calculate the 95 percentile, okay, shoulder to fingertip length. So from shoulder to the fingertip, for fingertip, we will measure that. So the mean lower arm length with the hand is, so you suppose you get 442.99 millimeters with a standard deviation of 23 millimeter for the lower arm length, okay, with the hand. Next, the mean upper arm, okay, or UA length is 335.8 millimeter, and is the standard deviation is 17.4. Then assumed correlation coefficient is 0.4. Okay, so the solution, we will just use this formula. Okay, m sub a is equal to m sub la plus m sub ua. Okay, so what is m sub la? So m sub la, it is the measurement of the lower arm length. Okay, then plus what is m sub ua? It is the upper arm length. Okay, so it is equal to 778.7 millimeters. Okay, so next we will get the standard deviation. Okay, so to get the standard deviation, we will just get the square root of our sum here. So we will first square the standard deviation of the lower arm length, plus we will square also the standard deviation of the upper arm length, 10 plus plus 2. So where do we get this 2? So this 2 is in the formula. So you can go back to the formula, the upper part of the module. So number 2 there is constant. And 0.4 is the R, okay, or the correlation coefficient. And of course, 23.4 is the SD, okay? And 23.4, again, is the SD squared. So you can go back to the formula to check if it is correct, okay? So the standard deviation is equal to 34.3 millimeters. Okay, so for the 95th percentile, we will just add the mean that we get 778.7 millimeter plus the 1.65. So where do we get 1.65? Remember the table, okay? So we can find it in the table. It corresponds to 95th percentile, okay? So 34.3, it is what we got. It is the standard deviation, okay? So the 95th percentile is 835.30 millimeters. So we should design the arm length to that, okay, to fit all of the users, okay? So some anthropometric guidelines. So the following figures illustrate the concept of recommended working zones of the hands and feet in a typical workstation. As you notice, the first picture, uh, the area in the grid is from his knees and to his toes. Okay, so that it only shows that uh, the area should permit the movement of the knees. Okay, and as well as uh, the toes. Okay, or the feet. So next, this is the upper view. So this is the side view first. Next, the upper view. So figure 4 recommended workspaces of feet. Okay, so those are recommended workspaces of feet. So they have enough spaces. Next, figure 5, recommended hands working zone. Okay, so you can see that this is the side view of it. Then this is the top view. Okay, so this zone permits the free movement of the hands. Okay, and of course the easy reach of the things that the user may need. Okay, so next. In terms of safety critical application, the distance of point of reach should include safety margin. Okay, so we have to include those. Safety margin. So the recommended safe distance between the working person's hand in the danger point would be the length of the longest arm and finger reach with safety margin at least 10%. So we will measure those and get the 10%. So it should be the distance from danger. Okay, the following figures demonstrate the recommended safe distance and safety margin. So this is the example. Okay, so this is the danger point. Okay, this box. So now it is measured here from the toe to the, what is this? To the elbow height. Okay, and of course uh, the distance between the person feet, okay, or legs to the danger point. So that's how you measure it. Okay, so this is the recommended safe distance between worker's hand and danger point. Okay, so that, look at this illustration, so that the worker's hand won't touch, okay, won't touch the danger side because of the safety margins. As you notice, this shaded part, they are that is the safety margin measurement. Okay, so that uh, the parts of the body of the users will avoid danger point. Okay, so workers are recommended to perform tasks at elbow height. So uh, at elbow height, it is the recommended for workers. So workers is sitting in sitting posture. The elbow height is measured from the elbow to the seat surface if the worker is sitting. Okay, not in the reference to the floor, unlike in standing posture. Because in standing posture, it's like it is it is as is in the picture. Okay, so in addition, determining working height needs to consider the degree of internal force to be exerted to perform the task. Okay, so it also uh, it uh, it The height affects the force that will be exerted by the uh, user. So the dimension of the workpiece itself and the visual accommodation requirement of the task. Of course, the dimension of the workpiece itself and the visual accommodation. So there should be enough accommodation and space. Okay. So for seating work posture, sufficient thigh clearance, so thigh clearance and leg room must be provided. Okay, for seating. So the designer may use the knee height, so from knee height plus shoe heels, so we will plus those as allowance as reference for the clearance. For standing workstation, advocate advocate two space, so spaces in the toe. Okay, at the bottom allows the worker to come closer to the workpiece so that the worker can come closer to the workpiece. The recommended depth of toe space should not exceed 10 centimeter. Okay, that's the recommended depth. And height of not less than 10 centimeter. Okay, so what is that? So the depth is uh, the the distance. Okay, the distance of the toe to the workpiece. Okay, and uh, the height of the the height of the workpiece to the with reference to the toe. Okay, that's why it is zoomed here. Okay, sitting and standing workstation. As you notice, those two toes has applied those requirements. Okay, so minimum max strategy, min max strategy. So what is this? The principle of min max strategy states that the tool and other components of work system must be designed to fit and accommodate the small and large members of the target system users as well as the everybody in between. So in this strategy, we have to get the minimum and the maximum measurement. So the goal of the designer is to properly determine the minimal or the maximal values for design limits, particularly for designs that need range of adjustments. So particularly for those who need more adjustment. So next, anthropometric measurement devices. So what are these devices? So grid board, as you see in the picture, it is a big board and blocks used to anthropometric measurement consists of sets of grids. So this is the same with the one you have watched in the video earlier, okay? And inside, corner to vertically walls or boards attached perpendicular with one another. So the subject responded for anthropometric measurement has to position in front of grids and the values of anthropometric variables are to be placed against the grids. Okay, so that is how getting the anthropometric measurement using this device, the grid board and blocks. Next, anthropometers are graduated rods. So they are graduated rods with a sliding edge at a right angle and normally used for bony landmarks that cannot be projected easily onto grids. Okay, so it's like a caliper. Did you see a vernier caliper? It's like that. It measures the thickness, okay, of the parts or the bony landmarks of the human body. Next, spreading calipers. So this is what I'm talking about. So the vernier caliper consists of two curved branches joined in a hinge, and the distance between the hips of the branches is read from the scale, while small sliding calipers are used to short measurements. So this picture on the left is used for a wide measurement, okay, while the second is for short measurement, such as finger thickness. So for only fingers and finger length, okay. So those are the calipers. Next, the most common and highly used anthropometric measurement, of course, every home I think has one of these, is the flexible tapes or the flexible meter tape, okay, and can be used in collecting data for circumference and curvatures. Okay, so if your parents have one of these that they use for sewing your clothes, you can borrow, okay, the flexible tapes. So next, goniometer is used to measure angular position and range of motion. Okay, so it is uh, a two ruler, and it is moving 360 degrees. Okay, so it used to measure the angular position. Next, in addition to direct measurement of anthropometric data, there are other indirect measurement methods in anthropometry. So what are they? What are these? So indirect methods is photography. So you can use uh, your cameras of your cell phone for photography. Okay. Then video recording. Okay, as documentation. Okay. Next, internal imaging. So what is internal imaging? So it is the one that is used in medical field. Okay. Do you know the ultrasound for uh, pregnant women? So it is like that, the internal imaging. So next, ultrasonic scanning. So it is also like the internal imaging by using ultrasound waves, okay, to scan the internal parts of the body of an individual. Okay. So next, magnetic resonance imaging (MRI). So it's a medical technique used in radiology. Okay. Okay. Do you see uh, have you seen a patient that is being transported into uh, a circular machine? Okay, that is MRI. And of course, the X-rays. I know that every one of you has experience in taking this. Okay, so lasers and optical surface scanning methods. So these are the indirect. Okay, guys, indirect measurement. So special devices, jigs and gauges. So the picture of jigs and gauges is like this. Okay, so there is a gauge. When you say gauge, it is measuring device. Okay, just like measuring the strength or the the power of an individual. Okay, this how much strength he has. Okay, so these are the example of jigs and gauges measurement tool. Next, the rod sets for measuring contours. Okay, what are those? So this is the example of it. Those fixtures. Okay, if you see the video a while ago, it involves rod sets in measuring body contours, wherein you can measure the anthropometric measurement of the body parts by using those fixed rods sets for measuring body contours. Okay. So next, and even casting. What is this casting? So it will be in the form of uh, getting the shape, okay, getting the shape of a body part, just like the arm. We can cast using the arm, okay, by some materials like plastic, okay. So next, electronic measurements, like electromechanical probes. So this is the example, okay? Just like in the ultrasound, you have these devices which uses the electromechanical properties, okay, to measure what is inside of the body, okay? Because there is some measurement that needs to be measured there, okay? Next is sonic digitization, okay? So this is the example of it, okay? So the digigraph uses sonic digitizing electronics to record cephalometric landmarks by tightly touching the sonic digitizing probe, okay, the patient's skin. Okay, so that's the measurement of it. And of course, the weighing scales. You are familiar with this, okay? Next, anthropometry and psychology. So there is a fundamental rule in anthropometry that relates to the discipline of psychology. So what is it? What it is? Simply asking people for their height and weight can lead to fairly reliable information. Okay, so we can do that. This rule comes from the conception that people with body disturbance image wherein uh, there are generally both women and men have a tendency to underreport their weight. Okay, but there are also individuals who overestimate their body weight and size. Some survey relating to the body image disturbance reveals that short people will be likely to overestimate their stature. So if you have a user that is a short height, he tends to he tends he is more likely to tend to underestimate his stature. Okay, so while heavy people often underestimate their weight, or if you have a uh, user that is overweight, so he or she tends to make her weight lighter. Okay, thus it suggests that self-reporting of anthropometric measurement load to inaccurate data. Okay, so it will be inaccurate. So we have to do those anthropometry measurements. Okay, so for the summary, the fundamental concept in the science of anthropometry, it states that one should design a system in such a way that tall people can fit and small people can reach. Okay, so the principle of limiting users is an important design consideration to accommodate greater percentage of user population. So how is that? When you are getting manpower, you should come up with uh, characteristics. Okay, so for example, you should hire or tell your human resource department to hire someone or workers with at least 5'5", okay, 5'5" in height. So you should limit your workers or your users. Okay, therefore the science of anthropometry is consistent with the paramount objective of ergonomics in designing systems that fit the workers and not the other way around. Okay, so it is in most important part of ergonomics, the anthropometry. Okay, so for the learning objective, the objective of the activity is to accurately measure body's dimensions in steady state. So it will be in a state with no moving bodies, okay, and correctly compute for the necessary statistic in an anthropometric design. So anthropometry is the measurement of physical characteristics of humans for the development of measures that accurately describe specific uh, populations. Engineering anthropometrics is the application of these measurements to the design of equipment for human use. So this is part of our work, okay, as an industrial engineer. When you become an industrial engineer in an industry, this may be a work the this may be the kind of work for you. Okay, so anthropometric tables typically present data for the 5th and 95th percentile measurements, as we discussed earlier, of the population. So along with the mean and the standard deviation of the measurement, however, it is often necessary to calculate additional percentiles. Okay, so for your activity, practice collecting anthropometric data from 3 to 5 subject respondents, okay? Preferably from your family members, okay? Your mother, your father, your brother, sister, or your small brother, or grandmas, okay? Your tito or your titas, okay? Get the following body dimension as shown. So you will just get this following body dimension, okay? You can use your flexible tape, okay? Because it is the most uh, used measurement in our homes. Okay, so first is the body dimension. Uh, you will measure this stature, the eye height. So there are labels. Okay, so you won't be confused where to measure. Okay, so per measurement here, you will measure 3 to 5 subject respondents. So to be fair, uh, uh, let's set it to 4. Okay, so 4 subject respondents. Okay, so each of these you should have 4. Okay, next, body dimension, body dimensions again. So they are labeled so that you won't be confused. Okay, all right. You will use this form, okay, for the findings for each individual anthropometric measurement. So this will be your laboratory number 1. Okay, so here are the references.